Hi, everybody. This is Scott from Redmond Tutoring.com, and welcome to the first published webinar of, I guess, autumn 2016. I have done one webinar prior to this, but I had forgotten to set up some of the technical stuff, and it turned out that what I was drawing showed up really, really small, so I haven't bothered posting that one to YouTube. This one will. And anyway, I'm still sort of figuring things out with this technology. And what I like about it is that I can actually answer real questions that you have and look forward to helping you pass physics. So in today's episode, I'm going to look at electricity and magnetism. And the reason for that is because I have a course on udemy.com, which I can actually, what I'll do is I'll share my screen and just show that with you. Entire screen. And so this was the problem before when I was doing this webinar, that it was actually showing two different things. And so what I really want to do is just not show me so much, but show you what you want to see. So fine. There we go. So this is what I see, of course. Now, if I go, I have this course on the Intro to Electricity and Magnetism, and it's published. It's a free course. And initially, when I created this course, and I have to find, here we go. Preview as a guest. This is what you see. And the funny thing is, this is the preview as a guest, but also if you just go to udemy.com and search for electricity and magnetism, you will find this course. So, of course, I'm logged in. Why don't I just do the actual udemy.com, so udemy.com, and then if you search for courses, electricity and magnetism, it will give you a bunch. And some of them are $30, $24, $24. Of course, this will probably change by the time you watch this, but I have a free one here, and it has just enough ratings to keep being listed. All right, so I have actually logged in as this because I'm a student and it recognizes that. But this is the free course. Now, initially what I want to look at is the course content, was that I just talked about electric fields and the electric charge and electric force. And the idea with that was that I was going to give that part away for free and then charge for another course for the rest. But I've decided instead to make the entire content that I've produced available for free. And I have 3 more chapters after electric potential. So what this means is that I've fleshed out the lectures on the electric fields to include the continuous charge distribution and the permittivity constant. And then we can look at Gauss' law and electric potential. And electric potential is the concept that students have the most trouble with. So hopefully this can help you do better in physics. I have 3 more chapters recorded after this that are ready to add. It just takes a bit of time to add them, which is the only reason I haven't done that yet. And I'm not sure yet whether I'm going to finish off this course with the rest of the content from the CEGEP curriculum. It really depends on how well these things go, because it takes a lot of time. And I realized that I believe anyway, that I can help you better by answering your questions than I can by finishing off this course. So I encourage you to go check out this course. And what I'm doing today with the webinar is I'm planning, using this program called Ink2Go, I'm planning to actually introduce some questions that I had on tests from prior. Here we go. So this is sorry, I'll say that again. I'm going to introduce some test questions and then show you how to solve them. And this is actually from a physics test that I gave when I was teaching. This would have been 3 years ago, almost not quite to the day, because I'm recording this in mid-September on September 13th. This is the 30th. So this is an example of the kind of test that I gave, and it included a formula sheet. And this was the same formula sheet that my students got for every single test and the final exam. So let's take a look at the first question here. Now, the question says that there are 2-point charges located as shown, and the charges are given 15 microcoulombs for the first charge, That's positive 15. So I'm going to circle that here in red. And negative 3 microcoulombs for Q2. So I can fill that in blue. So the first thing to do is find the position of a point other than at infinity where the net electric field is 0. The second thing, to find the position of a point other than at infinity where the net electric potential is 0. And students often confuse these things until you've actually spent some time calculating them. So really the answer to this is make sure you practice problems. And then part C is to say, are the points you found in A and B the same? Should they be? And to briefly explain why or why not. And I know students, in my experience, hated these kind of briefly explained questions because they felt it was very difficult to understand, or rather difficult to explain it in a way that would get full marks. And really, it comes down to understanding the difference between electric field and electric potential so that you can actually show that they should or they should not be at the same point. So this is the question. Let's see. The idea with any of these types of questions is figuring out what direction the electric field would be at different points. So what I'm going to do, I'm going to erase this so that I can zoom in here. I'll dedicate the screen to this for a second. And again, we had positive Q1 and negative Q2. So I'm using red for the positive charge, and I'll use blue to represent negative. And the first question is to find a point where, and find the position where the electric field is 0. So there are basically 3 different regions we can look at. So I'm going to just use a green dotted line there and a green dotted line in here. It basically, this point has to be on some line that goes through both Q1 and Q2. And I guess I could illustrate that just by looking at some point. So if we look at some point, I'll call this P, maybe P1, because it's the first point we're looking at. If we look at P1, the electric field at P1 coming from Q1, remember the electric field points away from a positive charge, is going to be up and to the right. So this would be E from 1 at P1. And the electric field caused by Q2 is going to be towards Q2 because it's a negative charge. So this would be the electric field 2. I guess I should label these P1 and then P1. I'm picky about labeling. Your teacher may or may not be. It's a bit annoying when you get E2, P1 when you have 3 subscripts there, but anyway. I just want to distinguish the electric fields at this point from Q1 versus the electric field at other points that we're going to draw in a minute, or I'm going to draw in a minute. Anyway, the reason I drew this out is to show that when you add these 2 vectors up, there is no possible way for the E1, P1 and E2, P1 to add up to 0 because they're on different lines. When you have only 2 vectors, in order for them to cancel out, they have to be opposite. So whichever direction you choose, they have to be opposite. If they're not opposite, then what happens when I add these up is that I start, say, with the first one and then going tip to tail, I would have E2, P1 there, and the net electric field would be to the right. And it's going to change slightly, actually a lot, because these charges have different values and it depends on the distance. So this isn't a perfect representation. It's not to scale, but it doesn't have to be because it's clear enough just to show that these 2 vectors are not on the same line, and so they cannot possibly cancel out. And that's actually going to be true on any point in space, except it might be possible for them to cancel each other out if it's on a line that is at y = 3 meters, which is going to be along this dashed line. So it's a line that goes straight through Q1 and Q2. I guess I could go off to the left as well. So if I look at a point over here, so I'll call that P2, then the electric field at P2 caused by Q1, it goes away from Q1. So that's E2, because it's the electric field at 2, caused by, actually, I'm messing up my notation already. That's the electric field caused by charge 1 at point 2. Then we could also have the electric field from Q2, which would go towards Q2. So this would be E2, because it's from Q2 at the second point. It's possible for those two to add up. If we look in the middle, call that P3, then we would have the positive electric field vector going to the right, and we would also have the negative electric field vector going to the right. So that would be E at point 3 from, this is at P3. Sorry, this is E2 P3. I should learn and use simpler notation. The electric field from charge 2 at point 3 and the electric field from charge 1 at point 3. And the last point to consider would be some point to the right of both charges. I'll call this P4. And in this case, then the electric field from Q1 is again going away. So away from Q1 now is to the right. So that's E1 at point 4. And the electric field from the second charge, Q2, is going towards that negative charge. So this is E2 P4. All right. The question actually asks us to locate the charge. And at this point, it's all very conceptual. We can see that in the middle case, at point 3, the two vectors are in the same direction. So it's impossible for them to cancel out. The electric field cannot be 0 in that region, no matter where we are in the region, because the vectors, they're going to change magnitude depending on how close we are to Q1 and Q2, but there will always be in the same direction in between the two charges. So the point where the electric field is 0 cannot be between Q1 and Q2. If we look next at P2, which is to the left of Q1, in this case, it's possible for the vectors to cancel out because they point in opposite directions. However, Q1 is the stronger charge. Remember, it was positive 15 microcoulombs. Q2 is a negative, well, it is a negative charge, but it's also the smaller charge. Q2 was negative 3 microcoulombs. And the electric field strength is given by the expression E is equal to KQ over R squared. So when we're out here, if we're closer to the bigger charge, that would mean that we would have a bigger Q and K as a constant. So we have K as a constant, then we would have a bigger Q, and then we have a smaller R because we're closer. And that smaller R gets squared. So the bigger Q, and again, this is sort of a hand-wavy explanation because we can actually figure out where it is, where the electric field could be 0, what region at least, without doing the math. But so we have a constant times a bigger Q on the top, and that bigger Q tends to make the electric field bigger, divided by a smaller R squared on the denominator, which also tends to make the electric field bigger. So if we're closer to the stronger charge in this region to the left of Q1, that means that E1 P2 is always going to be greater, and this is the magnitude, than E2 P2, which means that the net electric field cannot be 0. Because the red component is always going to be bigger than the blue component because we're closer to the stronger charge, which means then that the electric field can only be 0 somewhere to the right of Q2. So then we have to figure out where that point is. And I've gone through, and this has taken me a long time to explain, right? Because I'm going through carefully piece by piece. What you want to do before you're actually writing your own tests is practice these concepts enough that you can actually figure this out really quickly all on your own. And it takes practice. Physics takes practice. So now let's actually take a look at solving the first part. So for part A, we had to actually find where it is. And so then what I would say is that at some point, which is x, unknown in x, but it's where y is equal to 3 meters, the magnitude from E1 is equal to the magnitude from E2. And remember that in this case, we had E1 going to the right, and we had E2. In this case, we're closer to the weaker charge. E2 was going to the left. And this expression E1 is, basically, if they have the same magnitude, then the net electric field is 0. And so what we can do then is we can substitute into this. E1 is equal to E2. So we have K times our 15 microcoulombs divided by, and this is going to be R1 squared, is equal to K times, and we have 3 microcoulombs. Now notice I didn't put in the negative 3 here, and that's because E2 refers to the magnitude of the vector. And we have R2 squared. So this is the point, let's say P4. And then remember, we were closer to the negative charge and farther from the positive charge. And if I just, let's see, how am I gonna, I think I go back to page. There we go. So if I show this diagram again, in fact, it might be easier to see without that. Then P4 is to the right. And so this distance from Q2 to P4 is going to be R2, and this distance from Q1 to P4 is going to be R1. So if P4 is located at X, then I can say that R2 is equal to X minus 7, and R1 is equal to X plus 3. And I can solve for X. Another way to do this is to actually just notice that the distance between Q1 and Q2 is 4. And then you can say that R1 is equal to R2 plus 4. And then you can solve for R2. That's a completely valid way to set it up as well. I'm just looking at my math, and it's not necessarily better the way I did it. Anyway, I'll just stick with what I did for consistency. So I go back here. When I substitute in, then, in fact, at this point, I can cross off the k's because I have the constants on both sides. And in fact, I can cross off the units because we have times 10 to the negative 6 on both sides as well. If I was being really picky here, I could factor out, like divide 15 by 3 and have 5 and 1 as well. And I didn't do that, so I'm just going to stick with the way I did it to make sure I don't mix up the math. Anyway, so at this point, then, we would have 15 over, remember, R1 was X minus 3, and then that gets squared. And then I have 3 divided by, and R2 was X minus 7 squared. And so I'm expecting X to be bigger than 7 because point P4 is to the right. So we had X equals 7, X at P4, and then we had X equals 3 at Q1. Okay, so then if I have that, I can actually take the square root of both sides, just to get rid of the squares. And then I get the square root of 15 over x minus 3 is equal to the square root of 3 over x minus 7. Then I can cross multiply. Space on the right here. Yep, and then I just expand. So root 15x minus root 15 times 7, which will be 7 root 15, is equal to root 3 times x minus root 3 times 3. And the square root of 15 will be bigger. So I'll move the x's to this side. I have the square root of 15 times x minus the square root of 3 times x is going to be equal to, let's see, that's negative 3 root 3. And then I have to add 7 root 15 on that side. This ends up giving me 2.1409x. And I tend to carry 5 sig figs in intermediate calculations. 21.915. That's partly because I spent a lot of time solving online problems where it actually really mattered. If you were off by 1 sig fig and the 4th significant figure, then it would actually give you the wrong answer, and that was really frustrating for people. Anyway, so then I'm just dividing it out and I can solve, and I find that x is equal to 10.236. In this problem with 1 sig fig, I just round that off to 10 meters, but this is the final answer for x. I guess we would also have that y is equal to 3, and the units would be meters. So the net electric field equals 0 at x is equal to 10.2 and y is equal to 3 meters. And when I was in undergrad school, I went to school for engineering. We, in some classes, not all, but in some classes, we actually had to very clearly label our answer. And that was basically to help the teacher give us the grades, right? I recommend you do something like that. Like, I still retained the habit of putting a box around my final answer. And the reason for that is because I wanted to make sure that the teacher or the teaching assistant, and having been a teaching assistant, I really enjoyed being a TA. And so I put a lot of effort into marking, and I know a lot of teaching assistants don't enjoy it quite as much as I did. And even enjoying it doesn't, like, it's difficult to motivate yourself to do a really thorough job of grading because it's a tedious job. But it has to be done, and it's better if it's done well. Anyway, anything you can do as a student to help the person who's grading your work understand what the final answer is or understand your work, anything you can do to make it easier for them will help you get better marks. So it's really worthwhile to have some kind of a habit, or figure out, if you're in a course, figure out how your teacher wants things to be explained to make sure that you can get the most marks. Okay, the next part of this, the software is kind of neat because I can play around with showing different whiteboards and things. Let's say I want it. Okay, I need to zoom out a little more than that. Okay, the next question. So basically I can look at this. Maybe I'll try to freeze this here. So we found the electric field is equal to 0 over here at x is equal to 10.2 meters. Okay, so the next question was to find the position of a point other than at infinity where the net electric potential is 0. And then part C, we already talked about a bit. Should it be in the same place? So hopefully, I'll just introduce a new page here. Hopefully you recall, maybe I'll set this up. The remember the expression for the electric field magnitude was K times Q over R squared. And this is the electric field at distance R from a point charge Q, and K is a constant. For electric potential V, we can find the electric potential as KQ over R, which is different. It's almost the same, right? But R is squared for the electric field and R is not squared for the electric potential. So in this case, we want a point where V is equal to 0, which means that we want a point where V1 plus V2 is equal to 0. And another neat thing about electric potential is that it does not depend on, like, there's no direction. The electric field has a direction. Electric potential is a scalar quantity. So we need to find a point. We can say KQ1 over R1 plus KQ2 over R2 is equal to 0. We had, I don't know if this is going to work anymore. Yeah. Well, I guess I can show you this part. It's the one flaw with the software that I'm using right now called Ink2Go, that it doesn't tie itself to the PDF. But anyway, so if we set it up in terms of x, finding x and y again, then R2 is going to be x minus 7, R1 is going to be x plus 3. And this assumes, again, that we're working on a line between Q1 and Q2. Now, because they have different, I'm just realizing there's, find the position of a point. I wonder if there's an infinite number of points. The electric potential is 0. That gets much more complicated. I'm going to ignore that for now. So I'm going to assume it's on the same line and then let my mind sort of dwell on whether it could be in different points later on. So if we set this up such that R1 is equal to x minus 3 and R2 is equal to x minus 7, then we can again factor out the k's, because we can divide the whole thing by k. So if we factor out the k's, then we can substitute in. And so we have Q1 as 15 microcoulombs divided by, and then for R1, we had x minus 3. Q2 is negative 3 microcoulombs. And here we do need to include the negative over x minus 7, because we're not dealing with the magnitude of the potential in this case. This is equal to 0. Now, the next thing I could do would be to, I guess, cross off the microcoulombs again, because that's going to factor out. But I could take this whole term and move it to the other side of the equation, which would give me 15 over x minus 3 is equal to, and then I have to add that 3 over x minus 7. Then I can cross multiply, bring this over here. So 15x minus 7 times 15, 105. And I'm pausing here because I'm looking at my setup, because I set it up assuming that the math would just work out where x is. But I'm going to pause for a second, just draw this out for you. So if we have a positive Q1 here, and that was 15 microcoulombs, then we have a negative Q2, negative 3 microcoulombs, then what happens is that we're going to have our negative potential around the negative charge, like this. I'm going to have our positive potential around the positive charge. And I'm drawing these equipotential lines in roughly the same scale, except that the positive charge is bigger. It's 5 times bigger. There's 5 times more charge there, so it's going to be stronger. So what I'm looking for is a point where the positive and the negative can cancel out. And there could be multiple points for this. I think this is actually a poor choice of test question, looking at this right now, because you could have a point that's farther away from Q1 and close to Q3. You might be able to find a point over here where there's 0. In fact, I'm sure I could solve this and find that point. But what I was looking for, what I was expecting to get was a point in here. But when I have a point in here, then this one, R2, which is the distance between Q2 and the point, for here I would have R2 is equal to 7 minus X, because this point would be at X, this point would be at 7, and Q1 would be at 3. So R1 would be the same thing. It would be X minus 3. And if I substitute 7 minus X, I'm going to get a different result here. And I can propagate that through. Now that I've done this drawing, I'll change how this is set up. So 15 times 7, we would have 105 minus 15x is equal to 3x minus 9. So if I bring the positive x's together, I would bring it over to the right-hand side, and that would give me 18x, because I'd have 15 plus 3. And then 105 minus 9 is going to give me 96. But I forgot. I have to add 9 to both sides. So I get 114. And then solve for x, and I get x is equal to 6.33 meters. And that would be a point where the potential is 0. So there's nobody to complain about this right now. And I'm not surprised about that. I don't have many people lined up and eager to take these webinars just yet. And I'm hoping that by watching it on YouTube or just basically, I'm hoping to build the audience over time. And it's an experiment. Anyway, I don't have anybody else watching live right now. It's just me. So what I'm going to do is I'm just going to play around with it off to the side and look at what would happen if we had a point over here where we were closer to the weaker charge. Because 6.33, if we had, say, 4, 5, 6, 6.33 would be closer to 7, much closer to 7 than 3. So that would be actually in here somewhere. So it's closer to the weaker charge. And there might be a point over here to the right of Q3 where, in this case, R2 is equal to x minus 7. Remember, that was what I had at first. It might work out there as well. So what I would do in that case, maybe I'll just switch to blue. I'll take this form of the equations and just work with it from here. Then I would have 15 over x minus 3 is equal to 3 over x minus 7. I should have taken the next line. 15 times x minus 7 is equal to 3 times x minus 3. So 15x minus 105 is equal to 3x minus 9. I'm going to get a negative answer for x, though. I think that might be the clue. All right. This would have been simpler too if I'd already factored out the 3. Anyway, so 15, I would have to subtract 3, so I'd end up with 12x. And then to combine the 105 and the 9, I'd have 12x is equal to negative 114. No, that's wrong. I have negative 9 on the side. I know from experience that even astronauts make arithmetic. Anyway, they make mistakes with arithmetic like this, and it's not helping my ego at the moment. But anyway, so I have to add 105 to both sides. So negative 9 plus 105. See, I'm going to get a positive. Okay, that's good. Interesting. Negative 9 plus 105 is going to give me 96. And then I have 12. 96 over 12, which is just 8. Interesting. So there are multiple points, which is interesting. Oh, and actually I do have that. So I have my solutions here. I guess you can't see them. Maybe I'll just stop sharing for a moment. I have my solutions here. And I do have a note actually right here that says V1 plus V2 is equal to 0 at x equals 8, y equals 3, 2, which is a bit farther from each charge. Anyway, I want to go back to screen sharing, the entire screen, and make that big again. So there are 2 different points. One is between the 2 at x equals 6.33, and another point is beyond. And I suspect there might even be a curve around Q2 above and below where even the y components cancel out. And that cannot happen for the electric field because of the different components, but it can happen for the, sorry, I should explain that better. It can't happen for the electric field because of the vector components. It's impossible for the vector components to cancel out if their vectors are not in opposite directions, which means that the electric field can only be 0 on a point that's on a line between the charges. But it is possible for the potential to be 0 at different points, just because it's not based on direction at all. So question C asked, are these 2 points the same? The points you found in A and B the same? And should they be? And it turns out they should not be the same because the electric field and the electric potential are related, but they're different. The electric field, E, can be found, or I'm going to say comes from, the gradient of the potential function. So that in this case, because we're looking along the x-axis, it would come from the Vx graph. And more specifically, it comes from the slope of the Vx graph. So if we were looking at potential along x, then we would have, because we had a positive charge, and this graph would have to be at y equals 3. If we have a positive charge at x equals 3 and we have a negative charge at x equals 7, then we're going to have a peak up here, and then it's going to go down, but then we're going to have this valley down here, and then it's going to go back up. So there is a point in between where it's equal to 0, and it turns out that point is here, because when you add these two things up, we basically have, sorry, not E, we basically have that the potential is 0 here. Man, I don't know if you have those days when you have trouble spelling a difficult word like the. I heard that from Tony Robbins a long time ago, and I definitely having one of those days right now. So the electric field comes from the slope of the graph. We can find the electric field at a point by looking at the slope. And this is the x component, because we're looking at the Vx graph. This would be the x of v graph, I guess, actually. And one of the key things here is that the slope of a graph can be 0 where the actual value of v is not 0. And vice versa. The slope might be 0 where the value v is 0. So basically I can't draw this to scale right now. What we would do would be to actually plot the potential function for each of the two charges and then add them up to get the net potential. And then you would look at where the slope of the net potential is equal to 0. And the slope would have to be 0 to the right. Okay, so that's actually it for that question. So that took a good 40 minutes to explain live. Usually when I did tests like this, so this particular test here, I'm going to stop sharing again. So this particular test had, I don't know how many questions now, 5 questions. So there's that question, there's another question on solving for Coulomb's law. Actually, you know what? The easier way to show you this is to share that. And make it big. So this question had, I want it to be wider though. Yeah. So the second question, we had 3 charges that in microcoulombs, we had to draw vectors showing the direction of the Coulomb forces acting on each charge and the net force on one charge. So we had to look at Coulomb's law. The next question had to do with an electron passing between 2 plates. And I've solved this as a YouTube video problem, so I won't do this one. I'll just point to it in the Udemy course. It's kind of a bizarre question. Basically, we had a fly. Let's see. Imagine we had a fly over here. See how badly I can draw a fly. Looks a bit more like a bee. Anyway, you have a fly over there, and you have an electron coming in from the bottom. And then basically, you want the electron to hit the fly. So it has to deflect in between these plates and hit the fly. And so then we had to figure out a whole thing. And I've solved this as a YouTube video, so I won't do this one again. But I had some fun making this question, that's all. And the next thing is that we had to explain questions. Again, the students hated these kinds of questions. So describe an electroscope, induction, we had to sketch electric field lines and lines from these point charges. And we did that. This is not awful. And then we had 2 identical conducting spheres carrying in each separated. A third conducting sphere is uncharged. It's then touched to A and removed, then touched to B and removed, and you have to find the final charge on each sphere. And so that's a conservation of charge kind of question. And this, after that, actually, then we had short answer questions. So this was a typical test. This was the test number 1. And the reason I wanted to talk about this is because I just spent about 40 minutes going through in some detail how to solve the first question. And when it comes to a test, when I did a test like this as a teacher, I would actually write the test and choose my questions and then write it out, answer it myself, and make sure that I could do it in about a third to half the time, even writing detailed explanations, not necessarily taking the time to record a video of the solution, but I was still creating a fairly detailed set of solutions for the test. Because there are 5 questions and this test was intended to be written in about 100 minutes, it was a 1 hour and 40-minute period, you could allocate 20 minutes per question. So you want to be able to solve this even faster than I just did. And it should be possible. It should be possible. You don't have to take the time to explain every single thing. You want your solutions to be neat enough that whoever's grading can give you the best marks and recognize what you're doing, but you don't have to write out every single thing and explain repeatedly, which I was trying to on purpose because I'm trying to explain the concepts and make it easy for you to grasp. So I'm going to end it there for today. But if this is helpful to you, excuse me, if this is helpful to you, I would love to hear that. I would love to. I'd love for you to let me know. That would be fantastic. If this is helpful to you, if there are questions that you have that you would like me to solve, that would be great. I don't know if there's a video problem. Anyway, yeah, I look forward to helping you pass physics. Again, these webinars are an experiment that I'm playing with to try different things, and I hope that it can help you. So I'm Scott from RedmondPhysicsTutoring.com, and I look forward to helping boost your grades in physics. Good luck.